Start recording and we'll go to screen sharing. We still have one last topic to discuss, which is the biosphere. And when we think about the biosphere, keep in mind, think of sphere. You know, we know what a sphere is from math or some subject. And the biosphere refers to the entire Earth that supports living organisms. So you could think of the Earth as basically being like a beach ball, and that plastic layer on the outside of the beach ball, that's what supports life. Goes up to the mountaintops. There are some bacteria that actually float in the air a mile or two above the surface of the land. The highest mountain is roughly about 6 miles up. The deepest part of the ocean is about 7 miles down. And we do have some archaebacteria that live in cracks and crevices in rocks about 2 miles underneath the surface of the Earth. So if you go 9 miles down, about 8 miles up. So if you think of a layer about 17 miles wide covering the Earth, that's the biosphere, the part of the Earth that supports life. Now, if you think about when we discuss biogeochemical cycles, sometimes when we're talking about biogeochemical cycles, we actually have to get further up into the atmosphere or further down into the Earth, because we are looking at the geo part of the cycle as well. So let's remind ourselves briefly about what the carbon cycle looks like. So remember that we think of carbon as starting out as CO2, carbon dioxide in the air. And carbon dioxide in the air can diffuse into water. In fact, anytime you have those two gases in contact, or any gas for that matter, in contact with water, it will diffuse into water. Once it's in the water, it can diffuse out. You've probably all seen, white water on a stream or a river. Those bubbles are air bubbles that are coming out of the water as it goes over maybe rocks or down a waterfall or something like that. Carbon dioxide goes back and forth between the air and water. This is a relatively quick process. Carbon dioxide is taken out of the air by photosynthesis, which is also a fast process. And notice that photosynthesis occurs on land. It also occurs in the ocean. There's pretty good evidence that there's more net primary productivity, more production of organic materials in the ocean than on the land. It's not as obvious because it's a little more spread out, but there is a lot of primary productivity there. Once the carbon dioxide gets incorporated into carbon molecules, plants use that carbon to build their bodies. Animals eat plants, and then we get our carbon for our bodies from plants. Fungi do the same, protista do the same. But taking carbon dioxide out of the atmosphere via photosynthesis, putting it back in via aerobic cell respiration, those are very fast processes. So the biological processes are typically fast when we look at a biogeochemical cycle. The chemical processes are typically fast. What's slow is the geological processes, which in this case is sedimentation. Organisms dying, this shows in the water, but it could be on land. Organisms dying, their bodies not decomposing, being buried under mud. And if this happens, these organisms, as their bodies are compressed, the organic compounds are changed, and eventually their bodies can form oil, coal, natural gas, peat, all sorts of things that we refer to as fossil fuels. Now, under normal circumstances, the land above these fossil fuels, the kind of light brownish here, has to erode. It has to be worn away by rain or maybe windstorms or trees being uprooted. Something has to expose the oil and coal and natural gas. And then when we have a lightning strike in a thunderstorm, or we have just extremely hot weather, these materials can catch on fire without any match or anything like that, and they can burn. But the process of sedimentation and the process of wearing away the soil over the fossil fuels and returning that carbon to the atmosphere as carbon dioxide when they burn, that takes millions of years. Now, humans are interfering in the carbon cycle in two ways. One is we're cutting down plant material, particularly trees. Remember, we said that when you view the Earth from space, you can actually see the rainforest getting smaller and the deserts getting bigger. Well, when we cut down plants, fewer plants means we're not taking as much carbon dioxide out of the atmosphere, because that is what plants do in photosynthesis. Notice our diagram shows an arrow going back. Plants do carry out aerobic cell respiration, but they take a lot more carbon dioxide out of the air by photosynthesis than they put back in by aerobic cell respiration. So fewer plants, less CO2 is removed from the air. And then the other way people are interfering with the carbon cycle is it takes millions of years for sedimentation to change dead organisms into fossil fuels. And in nature, it would take millions of years then to expose those fossil fuels to the air and return that carbon dioxide to the air. People are digging up fossil fuels and we're using them. You know, oil is what we get petroleum from to power cars, to use to lubricate engines. Coal is used to run a lot of power plants. Natural gas is used commonly for heating. All these things have more than one use. The problem is not that we're using them, but that we're using them and returning their carbon dioxide to the air so much faster than would happen through natural processes. Normally, there's a balance between sedimentation and then between returning the carbon from fossil fuels to the air. People are returning those fossil fuels to the air much quicker. It's estimated that during your lifetime as an individual, you return as enough carbon to the air that took several million years to form. So we're basically decreasing the amount of carbon dioxide removed from the air and increasing the amount of carbon dioxide added to the air. So carbon dioxide levels are increasing. And we actually have pretty accurate records on this for about 45 years, 50 years. And in the 45 years or 50 years that we have accurate records, we have estimates from before that, but the technology for measuring carbon dioxide wasn't as accurate and it wasn't done on a very widespread scale. So we don't necessarily have good values. But we do know that since about 75, sorry, there were about 350 parts per million of carbon dioxide in the air. Keep in mind, carbon dioxide only makes up about 0.04% of the atmosphere, 0.04%. So less than 1%, less than 0.1%, about 1/25 of a percent. So not 25%, but 1/25 of 1%. So because of that, except for nitrogen and oxygen, nitrogen is about 78% of the air, oxygen is about 21%. For all the other gases, we usually express how common they are in the air as parts per million. So go back to around 1975 or 1980, and there were about 350 parts per million of carbon dioxide. Now there's about 410. So levels have gone up somewhere between about 20% and 33% just within the last 50 years approximately. Now, why are scientists worried about this? Why do we make such a big deal about carbon dioxide with global warming? Well, one of the things we know by studying paleoclimate, paleontologists study ancient life. Paleoclimatologists study ancient climates. One of the things we know is that throughout the history of the Earth, the more carbon dioxide there is in the air, the higher the temperatures are. So there's a very good correlation. And we can figure this out by looking at things like ice cores in Antarctica and various other things. So we know that carbon dioxide is closely connected with the temperature of the Earth. And we know that we're raising it very rapidly. And in fact, if we look at temperature records, we have good temperature records that go back much further than our carbon dioxide records. Because when we look at carbon dioxide, we have to do a chemical analysis to tell how much carbon dioxide is in the atmosphere. We've been able to measure temperature accurately for many years. We have good temperature records going back to the 1880s. And if we look at temperature records, what we see is since the 1880s, when we start to have pretty good records around the world. Before that, they're a little more sporadic. We don't find them everywhere. Global temperature has gone up a little bit over 1 degree Celsius, about 2 degrees Fahrenheit. Now keep a couple things in mind. 1 degree Celsius may not sound like much, and it isn't in a way, but average global temperature is only about 14 or 15 degrees Celsius. So when you think about it from that perspective, it's more significant. The other thing is, we know, again, from studying paleoclimatology, we're actually in an ice age right now. And when you look at ice ages, there are 2 different types of periods that alternate. There are glacial periods when the amount of snow and ice is increasing, and there are interglacial periods. And inter means between, so there's a glacial period, an interglacial period, a glacial period. In interglacial periods, the amount of snow and ice are decreasing. So right now we're actually in an interglacial period. Scientists argue about exactly how long until the next glacial period starts. But keep in mind, we are in an ice age. Anytime the North and South Pole are both covered with snow and ice, the Earth is considered to be in an ice age. And again, to reinforce the idea that a 1 degree Celsius change doesn't seem like a lot, from what we can tell by studying paleoclimatology, the last ice age was only about 5 degrees Celsius cooler than it is now. So not a lot. So a 1 degree Celsius increase or decrease is actually pretty significant when we look at the overall climate of the Earth. So why is carbon dioxide bad? Well, remember what we said about the atmosphere a moment ago. 78% of the air around us is nitrogen. 21% is oxygen. Less than 1% is other stuff. Most of that 1% is one of the noble gases, a gas called argon. But if we look, carbon dioxide absorbs more solar energy than oxygen does. So that's kind of the skinny on it. So let's look at how this happens. So this is something that's sometimes referred to the greenhouse effect, because in a way it works similar to the way that the glass in a greenhouse works. In a greenhouse, you have glass, and typically the glass has some kind of coating on it. And what happens is when sunlight goes through the glass and hits the greenhouse, the wavelength of the sunlight that's reflected changes. And the glass in the greenhouse absorbs some of that reflected solar energy. So this is why you can put plants in a greenhouse and you can start growing them late in the winter or earlier in the spring than you can plants outside, because it's actually warmer in the greenhouse than it is outside. Well, greenhouse gases absorb more solar energy than oxygen or nitrogen, the 2 big gases that make up almost all of the air around us. So if we look at the sun sends solar radiation to the Earth, and the solar radiation is in the form of shortwave radiation mostly. Remember when we talked about photosynthesis, we talked about the idea that radiation has two properties, wavelength and frequency. So shortwave has a short wavelength. So when that solar radiation hits the Earth, some of that solar radiation is absorbed by the ground or the water or the, whatever is on the Earth. Before it gets to the Earth, some of that shortwave radiation is absorbed by clouds. Some is reflected back out into space. And when the radiation that does reach the Earth hits the Earth, some of it is reflected. Not all of it's absorbed. And this makes sense because, again, remember when we talked about photosynthesis, you can't see absorbed radiation. You can only see reflected radiation. So this is why we can see the Earth from space. Now, when the sunlight is reflected out to space, one of the things that happens is that for a lot of the sunlight, the wavelength changes. And notice that when we look at wavelength, we're thinking about the difference between each of these little squiggles in the line. So you can see that the squiggles are longer in this. So this is reflected as long wave radiation, the wavelength and the frequency change. When this is reflected out to space, some of it goes out to space, but some of it is absorbed in a layer of the atmosphere called the troposphere. And the amount of this absorbed long wave radiation, this is what we're concerned about when we talk about global warming with carbon dioxide as well as some other greenhouse gases. Carbon dioxide absorbs more greenhouse gas, absorbs more of this long wave radiation than oxygen and nitrogen do. In fact, when we talk about greenhouse gases, we talk about something called the GWP, the global warming potential. And the global warming potential really is based on three things: how much of a gas we have in the atmosphere, how long that gas stays in the atmosphere. Some gases break down relatively quickly, some persist for decades or centuries, and how much solar radiation the gas actually catches. So this can tell us something about the global warming potential. And everything is compared to carbon dioxide. So when we're trying to calculate the global warming potential of a gas, what we compare it to is what happens if you would add 1 ton of carbon dioxide to the air and the amount of warming that this would cause over a period of 100 years. So carbon dioxide has a global warming potential or a greenhouse gas rating of 1 because everything is being compared to carbon dioxide. So in this, if you were thinking of this as a mathematical problem, this is the effect of carbon dioxide divided by the effect of carbon dioxide. Well, we know that anything divided by itself is 1. So in this case, if we end up with a rating higher than 1, this indicates that a gas will absorb, whoops, highlighted the wrong one. So a rating higher than 1 indicates we have a gas that will absorb more long-range radiation than carbon dioxide. If the rating is lower than 1, this indicates that it's less of a greenhouse gas than carbon dioxide. Compared to carbon dioxide, nitrogen and oxygen are usually given a global warming potential or a greenhouse gas rating of 0. They don't really impact it. In fact, if we didn't have any carbon dioxide in our atmosphere, we would be in trouble. The Earth's temperature would probably, on average, be about 20 or 30 degrees colder, which means it would be like living in northern Canada for everybody. Some carbon dioxide is useful, but it's not the most common greenhouse gas. The most common greenhouse gas in the atmosphere is actually water vapor. It's much more abundant than carbon dioxide is. And it does absorb more solar radiation. despite the fact that it absorbs more solar radiation, it's given a global warming potential of 0. And this is because it's only in the air for a short time. Now, this is a little bit of an exaggeration. Really, its global warming potential should be like 0.1 or 0.2 because of the fact that if water vapor absorbs solar energy, this warms the temperature of the earth. If we warm the temperature of the earth, more water evaporates, so that absorbs even more solar energy. Now, the problem that we have is at some point, as we're absorbing solar energy, we get more clouds in our atmosphere. And as we get more clouds in the atmosphere, more solar energy is reflected. So there's some scientific debate now about exactly how much warming water vapor would contribute to the overall picture. Because after a while, water vapor starts to cause reflection of solar energy. But there are many gases that have a global warming potential higher than 1. One is a gas called methane, CH4. And methane is one of the things that we find in natural gas. So it's a part of what we get from fossil fuels. Compared to some of the other gases that people might release into the air, methane has a pretty short lifetime. Methane is only in the air for about a decade. But during that decade, it absorbs much more solar radiation than carbon dioxide does. So it has a global warming potential of somewhere between 28 and 36. Now, the reason we have to give a range, that we don't have a fixed number for this, is it partly depends on how high up in the atmosphere this methane is, as well as some other factors. Now, notice that methane is a potential problem because if we look at the human diet produces a lot of methane. Does anybody know what type of food that humans raise that produces a lot of methane?
Cows.
Cows. Cows have bacteria in their digestive system. Remember that animals do not make cellulase. They cannot digest cellulose. So cows have bacteria in their digestive system, and the bacteria break down the cellulose in the grass that the cows graze on. And remember, cellulose is basically made of lots and lots of glucose molecules. So the bacteria use some of the glucose. They make some of the glucose available to the cows. But when they do this, one of the waste products that they make is methane. And they actually produce a significant amount of methane. Notice that methane is found in natural gas. So it's one of those weird headlines that you might think somebody made up. But occasionally, cows actually have an obstructed bowel, and cows sometimes explode. You know, if you think about natural gas, you've all heard about houses exploding when there's a natural gas leak. Sometimes the natural gas, if a cow can't get rid of it, there are several recorded cases of cows exploding because of a natural gas buildup in their bodies. So that's not one of those weird, not true things that's found on the internet. It actually is true, but it's weird. But as a result, if people were vegetarians, there would be a lot less methane being added to the air. Now, there's still bacterial decomposition, but the cows contain large, large amounts of bacteria. There's another gas called nitrous oxide, N2O. And a lot of industrial processes, a lot of agricultural processes produce nitrous oxide as a byproduct or a waste product. It looks like nitrous oxide lasts about a century. And again, it absorbs much more solar radiation than CO2. So this has a global warming potential of about 10 times as much as methane. somewhere in the 260s to around 300. And again, it depends on a couple of other circumstances. And at least to this date, the most powerful greenhouse gases that have been discovered are chlorofluorocarbons. So they've got chlorine in them, one of the halogens. They've got fluorine in them, another one of the halogens, and they've got carbon in them. They're usually just abbreviated as CFCs. And these absorb more solar radiation. And again, we're talking about that long range radiation that's reflected than any other greenhouse gas that's been studied to this point. Their GWPs are in the thousands, are tens of thousands. I don't know why I had tens typed twice there. So much more powerful. Right now, many countries have made it illegal to use CFCs in manufacturing processes, so that the amounts we're adding to the atmosphere are going down. But again, these chemicals have a long lifetime, so they tend to stay in the atmosphere once we add them there. You know, even if we look at methane, methane lasts about a decade. So if we could miraculously stop producing any methane now, we would still have methane in the atmosphere for at least another 10 years. For all of these, one of the problems is they persist. And this means that even if we stop making additional ones, the gases that we've already released in the atmosphere will be there forever. So the math is pretty simple. Basically, the math says if you add more carbon dioxide, more nitrous oxide, more methane, more chlorofluorocarbons to the atmosphere, we're going to absorb more solar energy. The Earth is going to get warmer. Now, keep in mind, this wasn't realized until about 1975. And it wasn't actually a climatologist who figured this out. It was actually an economist. And he was trying to look at how much carbon dioxide the industries in different countries produced. Because not only is it connected with climate, but the amount of carbon dioxide is related to how many fossil fuels you're burning. So it's kind of an indirect estimator of economic activity. So as this economist was looking at the amount of carbon dioxide produced, and I'm not sure why, but he was also looking at temperature, probably because he worked for an institute that tried to take cross-disciplinary approaches to studying things. But he noticed that there was a good correlation between temperature and carbon dioxide levels. And he started noticing that carbon dioxide levels and temperature were both increasing. And so this was the beginning of really our modern realization that global warming was occurring. Keep in mind that we're in a period where temperature should be relatively stable, or depending on how soon the next glacial period is, temperature should actually be cooling down slightly. So when the temperature is going up, this is kind of the reverse of what we should see according to the cycle that's occurring in nature. Well, one of the best ways to look at global warming is to think about the Arctic. If you look at the Arctic, you know, the North Pole, I hate to disillusion you if you're still hoping Santa lives up there, but the Arctic is covered by sea ice all year. And the reason it's referred to as sea ice is if we look at the Arctic, the actual North Pole is over open ocean. There are some areas to the north that are covered by islands. And so there's a little bit of ground up there, but it's mostly water. And you might remember from your history books, once the Europeans found North America, they sent a lot of voyages around the northern tip of Canada, trying to find what they called the Northwest Passage. And they wanted to get around Canada because that seemed to be quicker than sailing all the way down around South America. And what they were interested in was getting to Asia to trade. And they were never able to find a Northwest Passage. Why? Because even in the summer, the seas up in that region are frozen with ice. Now, when scientists in the early 90s first started taking global warming seriously, there were some estimates that suggested that the Arctic would be ice-free during the summer months by about 2050. So there would be some periods during the summer when enough ice would have melted that you would be able to take a boat and you would be able to sail from the Atlantic Ocean around northern Canada into the Pacific Ocean. However, it's good to study the Arctic for a couple of reasons. One reason is global warming is happening faster in the Arctic than in other places. Keep in mind, global warming is not happening at a uniform rate around the world. In fact, there are some areas, like Chicago is one. Most models of global warming suggest that as global warming occurs, the climate in some places like Chicago will get wetter and slightly cooler. Now, slightly cooler might sound good if we were talking about this at the end of summer school and it was, July and August, but it wouldn't sound so good if we were talking about this back in January. Now, the problem is, if we look at the Arctic, it's a good example of how we really don't understand a lot of the science that governs our own planet. Because when we started doing later studies, we found something called a positive feedback cycle. So let's think about what's happening with global warming. So temperatures go up a little bit because we add some carbon dioxide to the air. Now, when we add some carbon dioxide to the air and temperatures go up, if you're in the Arctic, what happens? Some of the ice and snow melt. Well, ice and snow have a very high something called albedo. And albedo refers to how reflective a surface is. If you've ever been outside or if you've ever been maybe in the mountains skiing sometime in winter, when there's fresh snow on the slopes, it can be almost blinding. A lot of people who are skiing or hiking in the snow wear sunglasses because there's so much reflection off the ice and snow. So ice and snow don't absorb very much solar energy. They reflect most of it back out to space. But when the temperature increases slightly because of global warming, snow and ice start to melt. Well, what's under the snow and ice? Well, if you're in the Arctic area, mostly water, but sometimes land. Whether it's water or sand, something very similar happens. Water is blue because it scatters blue light. It doesn't reflect blue light. So water absorbs more solar energy than snow and ice do. Sand, rocks, the things that we find on land are brownish or grayish. Why? Because they're absorbing some solar energy. So when ice melts, what happens? It exposes water, it exposes land. And what do those things do? They absorb more heat than the snow and ice did. So because they absorb more heat, this causes an additional temperature increase. Well, what does an additional temperature increase do? An additional temperature increase melts more snow and ice. So there's more water, there's more land exposed. So what happens? We absorb even more heat. So this is what's called a positive feedback loop. And positive feedback loops tend to continue until something breaks one of these processes. Now, if humans don't do something to decrease global warming, what will break this process eventually is there will be no ice or snow left to melt. So temperatures will continue rising, but we won't have the other factors occurring. So when we look at this positive feedback loop, temperature goes up, snow and ice melt, we expose more water and land, we absorb more heat, temperatures go up again. So when we look at this positive feedback loop, and basically you could think of a positive feedback loop as being more A gives us more B gives us more A. When we look at this positive feedback loop, the Arctic is warming faster than we would have predicted before. And then a few years after that positive feedback loop was discovered, biologists discovered another positive feedback loop occurring in the Arctic. Remember, in the Arctic, we have that permafrost, just anywhere from a few inches to a few feet underground in the tundra area. And so as the temperature of the Earth warms, the temperatures going up causes the permafrost to thaw out. Well, you might remember that one of the things we said was frozen in the permafrost were bodies of lots of living organisms, organic material that didn't decay completely. And it didn't decay because it was frozen. When the ground starts to thaw, bacteria can decompose it. And when the bacteria decompose that organic material, they produce some carbon dioxide and methane. So the amount of carbon dioxide, CO2, and the amount of methane, CH4, in the atmosphere increase. So if the amount of carbon dioxide and methane increase, what happens? This causes another temperature increase, which means we melt more permafrost, which means we thaw out more organic materials, which decay. So again, we have a positive feedback loop. Now, what's the short story on these two positive feedback loops? Most people think now that instead of taking till maybe 2050 for the Arctic to be ice-free during its summer months, it will probably happen by 2030 at the latest. And it's come pretty close to happening already. Some people debate and say it has happened, but there's not really universal agreement on that. Now, what's the problem with this? Well, if global warming continues, there's the potential not just to melt some of the ice and snow in the Arctic, but in particular to melt the ice and snow on Greenland and Antarctica. When ice that's already in the water melts, there's no change in the level of the water. That's because the ice, think of an iceberg, how some of it is underwater, some of it is on top of the water. Ice and snow, when they're basically in the water, they displace the same amount of volume as the water that's created when they melt. But the water that's in the glaciers on Greenland and Antarctica is over solid land. And if that water melts, when that water runs into the ocean, that will cause sea levels to rise. How much? Well, the estimates vary a little bit, but the general agreement is that sea levels will rise at least 67 meters, which is around 200 feet. Now, you have to keep in mind when we say that sea level rate is going to potentially go up 67 meters. We're not talking about the shoreline will be 67 meters in from where it was. We're talking about the water will be 67 meters higher. So basically as high as a 20-story building. And if you look at most beaches, think about any beach you've been on, even here in Chicago, the land on a beach usually slopes very gently. So the usual estimate is that if water levels go up 67 meters, the water will go about 670 meters inland, which still might not seem like a lot to you. That's a little bit over a third of a mile. But keep in mind, if you look, for instance, at the state of Florida, if water levels go up 67 meters, about a fourth of the state of Florida will be underwater, not on the shoreline, underwater. You know, if we look around the world, if you look at just places that are capitals of countries, Amsterdam, Bangkok, Nassau, Havana, Manila, Buenos Aires, Oslo, London, Tokyo, Jakarta, Brussels, Washington are all about 20 feet above sea level. If you look at the country of the Netherlands, there's that famous old myth about the little Dutch boy with his finger in the hole in the dike. They actually do have dikes in the Netherlands because most of the country is below sea level. If you look at the country of Bangladesh in Asia, the country, almost all of it, is a very gradually sloping plain leading down to the ocean. And if water levels go up 67 meters, then the ocean will probably move in several miles. So this is a huge problem. It's estimated that if water levels go up 200 feet, there will be several 100 million climate refugees created. People where they live now, their residences are underwater and will have to move to new spots. So we know global temperature has gone up at least a degree since we've been keeping good records. Now, the various agencies that have been studying this have set a goal to try to limit the temperature increase to 2 degrees Celsius. Because most of the really bad effects of climate change, which is just the politically correct way of saying global warming, but most of the drastic effects of global warming will happen if temperature increases go higher than 2 degrees Celsius. Now, keep in mind, temperatures have already gone higher by 1 degree Celsius. And about 3/4 of that change has happened in the last 30 or 40 years. Now, when the different agencies have tried to decide, what should the ultimate temperature be, there have been some disagreements. If you're saying that you're trying to stop global warming before the temperature rises 2 degrees, where do you start from? Some people have started from the 1880s, where we have good temperature records. If we start from the 1880s, we're already at about a 1.2 degrees Celsius increase. Some people have said, well, we should start this 2 degrees from where we are right now. Most climatologists think that that's too big a jump if we add 2 degrees onto the 1.2 degree change that's already occurred. Now, keep in mind, like with most ecology problems, the real question here is, can we limit our production of carbon dioxide? Because think about what we're doing that puts carbon dioxide into the air. We're burning too many fossil fuels. So are people really willing to walk to the store or ride a bike to the store or carpool to work or do some of the things that we know could produce less carbon dioxide? Scientists are working on something called carbon sequestration. And in sequestration, scientists are trying to come out with chemicals that would pull carbon out of the air and lower the amount of carbon dioxide in the atmosphere that way. Right now, they haven't got a way to do that that's really efficient. The problem right now is all the chemical methods for pulling carbon dioxide out of the air require a lot of energy. So where do you get energy from? Fossil fuels. So they actually put more carbon dioxide into the air than they remove. Now, it might be that at some point we'll find a method of doing that, but right now we don't really have a good one. Some of the other ideas for limiting global warming really sound more like science fiction, but people have proposed putting large mirrors into space, satellites. And these mirrors would reflect sunlight back away from the Earth. So not as much sunlight would reach the Earth. So then we could still continue producing as much carbon dioxide as we wanted, and it wouldn't have an impact. There's an idea that's even more bizarre than that. Some scientists have suggested that one way to lower the amount of carbon dioxide in the atmosphere is by triggering volcanic eruptions. We know when volcanoes erupt, they put small particles into the atmosphere. And when some large volcanoes have erupted, they've done so in historical times, and we've actually been able to measure a decrease in the temperature for a year or two afterwards. So some scientists have suggested kind of triggering some volcanic eruptions and using those particles that they put into the atmosphere to lower the temperature. Of course, you have to hope you don't live near one of those volcanoes if we decide to adopt that method. Now, the other possibility is obviously developing what's called clean energy, wind power, solar power, things like that, instead of using fossil fuels. But notice that there's a big economic disincentive to develop clean energy. Think about all the big oil companies and all the money that they spend on lobbyists. Their profits will drop if we're not buying as much gasoline. In fact, actually, one of the best things that's happened for the climate is what we're experiencing in this very class. The fact that for the last year or two, depending on where you live, people have been mostly working from home, going to school from home. People haven't been traveling as much. Fossil fuel emissions have stayed about as stable as they have in the last 50 years. Now, despite that fact, if we look at the 20 warmest years on record, so keep in mind, we have good climate records since about 1880. So we're talking about roughly 140 years. The 20 warmest years on record have all occurred since 1990, most of them since 2000. So even though COVID has been good for the environment, maybe nothing else, but it hasn't done much. The global temperature is still increasing. It's not increasing as fast as it was. Now, I've picked on global warming, but notice there are some other environmental problems that are similar. I'm sure you've all read about the microplastic that's in the ocean that we're finding in the bodies of fish. And you may not be aware, I don't know if you know what a product called Teflon is, but there's a product called Teflon that's put on nonstick cookware, some nonstick cookware. Almost all people in the United States have measurable levels of Teflon in their blood. Now, people are living longer than ever before, but at the same time, when we find chemicals like Teflon in our blood, you have to wonder if maybe this is somehow related to something like cancer or Alzheimer's disease or some disease that's been increasing. Maybe it's caused by Teflon, and Teflon is not the only man-made chemical that's found in your blood. So with environmental problems, because the chemicals in question, like carbon dioxide, can spread around the world in the air, because the microplastics in the ocean float everywhere in the ocean on currents, these are global problems that have to be studied at the level of the biosphere. Or if we go back to something we talked about at the beginning of our discussion of ecology, population biology. The human population is expanding, and no population can expand indefinitely. Remember that J-shaped curve ultimately changes its shape. And if people don't find a way to limit our growth rate by decreasing birth rate and consumption rate, nature will find a way to increase our death rate. So that's the cheery message I will leave you with today. Are there any questions about global warming or the greenhouse effect before we leave? Okay, this is the last lecture we're going to have. So tomorrow morning, I will have some questions posted on ecology. And when those questions are posted, you'll have a week to work on them, like usual. check your averages in the grade section. You can see where you are. This assignment is worth about 250 points, depending on if I change anything when I do my final edit after we get done. The other thing I want to tell you before you leave, keep in mind, next fall for science classes, if you're still at South Suburban, we will be back on campus for labs. And whether you're at South Suburban or someplace else, if you have other biology classes that I can help you with, or any other type of science, once you're in my class, you get free tutoring from me as long as you want. So a few years ago, I had a student who, after South Suburban, went to Purdue Cal and came back to see me regularly to do her math. And one year, I actually had a student who called me from USC all the time, but she eventually found a boyfriend who was a science major, so she dumped me. So keep in mind, if you have any questions in the future, feel free to contact me. But for now, I will let you go, and I will log on tomorrow at 9. If you have any questions, you can talk to me then, but you don't have to log on if you don't want to. So I'll send you an invitation like usual, but in the invitation I'll put, optional. So enjoy the rest of the day. It looks like it might be a nice day today.
Okay, have a good day.
You too. Bye-bye.
Have a good day.
You too. I will.
Have a nice day.
Bye-bye.
Have a good day.
You too.